All right, guys, in this mini lecture, we are going to go into detail regarding the concept of quantum numbers. So remember, quantum numbers can be thought of as addresses or labels that allow us to identify specific orbitals, which are quantum mechanical descriptions of atoms. And so these orbitals, as you recall, we denote them by psi, showed up as solutions to this little equation here called Schrodinger's equation. So we do some math, right? We'll plug it into our little magical math machine. You plug through that and you're going to come up with this psi, which is an orbital. And we recall from the previous lecture that there's a couple features of this set of orbital solutions to the Schrodinger equation. First off, there are an infinite number of these orbitals, okay? And these orbitals can be interpreted as related to a probability distribution, all right? Specifically, we saw that if you take that modulus squared of psi, which is just taking psi times its complex conjugate, we get a probability distribution. Okay, so there's an infinite number of these guys, and there's a probabilistic interpretation of each one of these solutions. And we're going to go into those details here in a minute. For right now, what we want to focus on in this lecture is just being able to identify unambiguously each one of these infinite number of orbital solutions. Okay? All right, so we're going to be doing this with quantum numbers. Once again, there are three of these guys. Okay, they have kind of strange names, and the names will make more sense as to why they have them later on. For right now, just accept it. We've got three numbers, right? These numbers are denoted N for the principal quantum number, L for the angular momentum quantum number, and M sub L for the magnetic quantum number. Now, as promised, we are going to basically completely ignore the mathematical details associated with these wave functions psi. We're going to instead focus in on the relationships between these quantum numbers and in fact be able to capture or really describe an efficient way for referencing all of these different wave function solutions. Okay, so here's the extent of the math for this section. Okay, these quantum numbers, it turns out in order for these orbitals to be solutions to our Schrodinger's equation, these quantum numbers can only come in certain well-defined recipes. Okay, so N, first one up, N, the principal quantum number. It turns out N can only take values of 1, 2, 3, 4, and all the way on up to infinity. So N must be an element of those positive integers. Okay, so could you define a mathematical function with an N equals 0? Yes, you could get a mathematical function, but it would not satisfy Schrodinger's equation up here. So in order for these wave functions to work, to be valid solutions, then you must be limited to only positive integers for that principal quantum number N. Okay? Then, once you have a principal quantum number N, that places constraints as to the values that the other quantum numbers can assume. So the first one up, angular momentum quantum number, denoted by an L. So if you have a given value of N, then the only values that L can take are 0 and then all integers up to N minus 1. Okay? Furthermore, the values of L then limit the possible values that our third quantum number can take. So our magnetic quantum number M sub L is constrained to the range of minus L and then all integers up to 0 and then all integers up to a positive L. So one way I like to illustrate what's going on here is using these little tree diagrams. So if we start off and we look at the first orbital that has an N equals 1, well, if N equals 1, we can ask ourselves, according to this rule here, what are the possible values that L can take? Well, L starts off at 0 and can go all the way up to N minus 1. Well, if N is 1, 1 minus 1 is 0, which means all we can do is get 0. The only possible value of L with a principal quantum number of 1 is 0. And then, of course, in a similar fashion, if we look at the possible constraints on our m sub L down here at the bottom, m sub L can go from minus L to positive L, but L is 0. So we're going from minus 0 to positive 0. Of course, all we have in that region is just 0 itself once again. Okay, so things get a little bit more interesting as we go to higher levels of n. If we jump up to an n equals 2, then according to our rule here, we can assume values of either an L equals 0 or an L equals 1. If L equals 0, then m sub L is still nice and boring. You only have one possible value of m sub L, namely 0. But if L equals 1, then we can take all values from minus 1 up to positive 1, catching all integers in between, including 0, and we are left with 3 different possibilities. Okay? So notice how the first branch of our n equals 2 looks a lot like the n equals 1 branch, 0, 0. Okay? So if we extend this again to an n equals 3 principal quantum number, then we again get that 0, 0 branch. We get the 1 with the minus 1, 0, plus 1 branch, but now we have yet another branch because now the possible values of L has been extended by 1. We can go all the way up to n minus 1. Now n is 3. 3 minus 1 is 2. So we're getting 0, 1, and 2. And then m sub L assumes all possible values ranging from minus L to positive L. So we get a minus 2 all the way up to a plus 2. Okay, so let's look at an example problem. In this problem, we want to figure out how many different possible orbitals have a principal quantum number of n equals 2. Okay, so if we have n equals 2, what we want to do is use our rules here, and we're going to build up a little tree diagram like we did in the previous slide to try and come up with all the possible orbital solutions. So n equals 2, that places constraints, of course, on the possible values of L. L can be any value from 0 all the way up to n minus 1. n is 2, 2 minus 1 is 1, so L is going to be 0 or 1. Then we can apply our third rule down here for assigning values to that magnetic quantum number. And of course, that is directly related to the possible values of L. If L is 0, then m sub L, the only possibility there is an m sub L that is 0. But in the case of L equals 1, we've got a few different options. We can have an m sub L as minus 1, 0, or plus 1. Okay, so if we list out the possible orbitals that we've constructed, well, it amounts to basically following each one of these little branches in the tree. There's going to be one branch where you have an n equals 2, L equals 0, and m sub L equals 0. And so we're going to denote that right here by a 2, 0, 0. Okay, using the notation listed here, n, L, m sub L. Okay. Similarly, if we follow down this next branch and we go down, say this one here, we're going to have an n equals 2, L equals 1, m sub L equals minus 1. That, of course, corresponds to this solution. And we have this branch here and this branch right here. So we've listed out all possible orbitals, and then we can count them up. We've got a total of 1, 2, 3, 4. 4 different branches. So the answer to our question is 4. There are 4 different orbitals, all of them listed right down here, that have a principal quantum number of n equals 2. Okay, so let's look at a slight variation of this problem. Okay, in this problem, I want you to determine how many different orbitals have an angular quantum number of L equals 2. So this would be a good time to go ahead and pause the video and see if you can answer that question. Okay, so just like we saw before, we're going to go ahead and proceed by building up one of these little pathways, branching diagrams. So I'll do it vertically here to try and save some space. So whatever the value of n is, it really doesn't matter in this case because we know that we are looking at only the branch that has L equals 2. So we're starting off with whatever n, we know we're going to L equals 2, and then we're tasked with basically coming up with what are the different possible values for that third quantum number m sub L. Well, according to our third rule up here, we know that the different values of m sub L correspond to the values of a range of values from negative L all the way up to positive L. So we can start off here and list negative L, negative 2, then we're going to have a negative 1, then we'll have a 0, then we'll have a plus 1, and then we'll have a plus 2. And each one of these branches corresponds to a certain solution. And so we can list out all those solutions down here, where again, a given solution corresponds to basically following the branch. Although now we're leaving that principal quantum number as just whatever variable n, right? Whatever integer it happens to assume. Now you can test yourself here. What values are we constrained to in terms of n? So once again, pause the video real quick and see if you can identify what possible values n can take. Okay, so the answer is, of course, based on the fact that we are dealing with an L equals 2. Because L is equal to 2, we know we must have an n that is greater than or equal to 3. Okay, so our n is greater than or equal to a value of 3. But it could be anything. So we're going to leave it as a variable n here. And then we build up the following set of 1, 2, 3, 4, 5. 1, 2, 3, 4, 5 different branches. So we have a total of 5 different orbitals. Okay, so that's the basics for building up these little orbital labels using quantum numbers. In the remainder, the last slide here, what I just want to do is introduce some common notations and definitions that we use when we're talking about these different orbitals with different sets of quantum number labels. So the first definition we have here is this concept of a shell. So a shell, and when we say, we refer to a shell and an atom, and later we'll actually see molecules as well. The shell for an atom is basically given by the value of that principal quantum number n. And so an atom could have many different shells, and we'll explore that more in future lectures. But each one of those values of n that a given atom has is referred to as a shell. So we have an n equals 1 shell, an n equals 2 shell, n equals 3 shell, and of course there's an infinite number of these. Okay, and then when you look at the different values that L can take, we refer to those different values of L and the corresponding orbitals as so-called subshells. Okay, so n determines the shell, L determines the subshell. And so, of course, according to our quantum rules here, there are going to be n minus 1 different subshells for any given shell n. And for some historical reasons that are rooted in spectroscopy, we have some little letter designations that we use for referring to the different subshells or the different possible values of L. So if L equals 0, we talk about this orbital description as being an s orbital. Okay? If we have an L equals 1, we talk about that orbital as being a p orbital. N equals 2, or L equals 2 is referred to as a d orbital, and L equals 3 is referred to as an f orbital, and then it follows the alphabet from here on out. These are the 4 orbitals that we're going to be focusing on, however, in this class. And so these letters correspond to, the text over here on the right, sharp, principal, diffuse, fundamental, and these are all descriptions that describe the emission spectrum that are associated with transitions like we talked about in a couple lectures ago involving these different quantum mechanical states or quantum mechanical orbitals. So that's sort of a sub point here. What you really need to remember is just this core correspondence here between a value of L and a specific letter designation. Okay, so a quick example here to round out this mini lecture. So let's basically do a quick run through of a handful of different orbitals and come up with the orbital name and the number of orbitals in this set. So the first one I have here has a principal quantum number n equals 2, L equals 0, and m sub L. So the orbital name we are going to assign uses that principal quantum number, carries it over, in this case is 2, and then includes the letter designation that corresponds to the given value of L. In this case, it's 0. Okay, so L is 0, which corresponds to an s orbital. So we're going to call this orbital with this specific set of 3 quantum numbers a 2s orbital. And then we can go over here and count up the total number of orbitals that will have this orbital designation or orbital name of 2s. To do that, we need to look at the different values m sub L can take. Well, if L equals 0, the only value m sub L can take is 0, so there is in fact only one of these orbitals with this specific orbital name. So coming through doing the same thing here, we've got an n equals 2, so it's going to be a 2. This time L is equal to 1, so we have a p, so we have a 2p orbital. And now if we look at the different values m sub L can take, we're going to have values of -1, 0, and 1, which gives us a total of 3 different orbitals. Okay? And so moving through here, we've got an n of 4, we've got an L equals 2. So remember, L equals 2 corresponds to a d orbital. And if we look at the possible values m sub L can take, we're going everywhere from -2 to +2, including 0, right? Which means we're going to have a total of 5. And so we can note as these numbers start getting bigger, it's nice to note the relationship mathematically that allows us to predict the number of orbitals. So that relationship is simply 2 times L plus 1. So it corresponds to just taking, all of the negatives of L, all the positives of L. So we get 2 times however many L you have plus 1 because we have that possible m sub L value of 0. So we're going to get a 5 for that one. And then for our last one, we're still up there at an n equals 4. And then in this case, we have a f orbital because our L value is 3 in this case. And then if we nail down the value of m sub L as we did here, well then we know the exact orbital state that we're talking about. So there's in fact only one orbital with this specific set of quantum numbers, this specific label. Okay, so I know that this chapter is a bit abstract and these rules seem a bit strange at first. So what I'm actually going to have you guys do before you start working through the problems is go through the next video, which presents another little analogy that will reinforce the concepts that we just talked about.